Hello, everyone. My name's Benjie. I'm a community-funded open-source developer working in the GraphQL, Node.js, and Postgres ecosystems. It is my absolute pleasure and privilege to be here with you today, speaking alongside all the incredible people that we'll be seeing, talking about the various technologies that will shape the future of software development. There's at least 8 talks, including this one, that relate to GraphQL at this conference. And rightly so. I fell in love with GraphQL 3 years ago, after 15+ years of building and consuming APIs. And my feelings have only gotten stronger. My main open source project is called PostgreSQL. It looks at your Postgres database, and it helps you to build a highly customizable GraphQL API very rapidly. I'm also a contributor to the GraphQL specification working group, and I help to maintain the graphical GraphQL IDE software, and I have various other projects in the GraphQL space. But I'm not the only one passionate about GraphQL. Since its release in 2015, GraphQL has been growing in leaps and bounds, fixing the problems of the biggest and the smallest companies alike. And I'm certain that we will see it continue to grow over the coming years. With its shiny new technology, skyrocketing growth, and huge impact, it makes complete sense to see GraphQL well represented at ReactiveConf. But it might seem strange that my talk is also about Postgres, a relational database system. Even at my age, it seems like relational databases have been around forever. How do they fit into the technologies that will shape the future of software development? Well, it turns out that relational databases have been shaping the future for at least the last 30 years, and are continuing to do so without no signs of slowing down. They are everywhere, from the biggest internet-scale companies to that save game file on your computer. They're in your TVs, on your set-top boxes. They're in your smartphones and in your car's multimedia system. In fact, many of us are wearing relational databases on our wrists right now. The term relational database was coined in 1970, but they really started to get big in the mid-'80s. By the mid-'90s, they were the dominant technology for large-scale data processing, and they still hold that position today. In the 2000s, as the web began to get more dynamic, it was natural to build our web applications on top of this pervasive database technology. Server-side languages such as PHP would construct the web pages and turn them into HTML and send them over the internet to the web browser to be rendered. Databases weren't really as advanced back then, focusing primarily on their central role of data storage. So many people and engineers would treat the database as basically a glorified spreadsheet with the columns and the rows and the tables like you have tabs in Google Docs. The application layer, the layer that sat between the end user and the database, written in a language like Ruby, PHP, Perl, or Java, was responsible for implementing the business logic, the access control, and other related concerns. And this worked pretty well. Enter the 2010s, and frameworks like Backbone.js, and later React, Ember, Angular, Vue, and various others began to take center stage. As JavaScript and the languages and the frameworks available within it became more and more powerful, websites started moving their rendering logic from the backend to the front end. Let's look at an example. Imagine that we've built a fully client-rendered blog. For the purpose of this example, we're going to pretend that we're using React on the front end and a Rails API on the back end, but the pattern is similar for many other languages and frameworks. Now we want to add a feature to our blog. We want to give users the ability to comment on our posts. This might look something like this. First of all, we need somewhere to store the data. So we're going to use something like a Rails migration in order to create a database table like this one. This one allows us to have a reference to the post that the comment relates to, the author of the comment, and the text of the comment. We need to represent this database table in Rails, and for that we'll use a model, such as this one, again stating that we have the relation to the post and the author, and noting that certain of these are read-only fields. We shouldn't update them. We need a way of sending this data to the user, and for that we'll use a view, or in Rails, a serializer, to tell the framework how to take this model and to export it to the end user. And at this point, we'll take the opportunity to maybe rename a few fields. If they were in snake case and we want them in camel case in our API, we might remove certain fields we don't want exposed or add additional information that might be useful. We need a controller to describe which actions can take place. And we need to expose those actions via something like a router so that our client can actually issue them. Now, parts of this process we've just seen can be templated, but a lot of it requires human intervention, especially later on if we get performance issues. We might get issues like the n+1 problem, or maybe the opposite. Maybe we're fetching too much data, and that's giving us issues. And for that, we may need to consult our old friend, Stack Overflow, and figure out what the best way of solving this problem is. In the client, the story is similar. We need a model to represent this data that we fetched from the API. And in TypeScript, it might look like this. In Elm, it might look like this. But we've probably had to define this model by hand, since we don't have a way to automatically generate it from our RESTful API. We also need to manually write the code that coordinates the fetching of these related data models from the server. And that needs to handle things like chained fetching, network errors, and maybe has something in it like some retry logic, so we can handle those errors and still display something to the user. We also probably need to write the code to handle our mutations. And in order to build those, we need to know what mutations the backend allows. And for that, we'll probably have to consult the backend documentation. I hope it's up to date and that it tells us what the type of inputs expected are. So we've just written a lot of code, and we're not even going to be able to deploy it anytime soon because of the amount of both manual and automated testing that we need to do to give us confidence in the software that we've written. For a typical web application backed by a relational database, probably about 80 to 90% of your API will be like this. Fairly straightforward mappings from the database types all the way through to the front end. And this is true for things like customers, products, notifications, emails, teams. Very many of your database tables represent your business domain objects. And they are then used throughout the entire stack. Sometimes you might need to add or remove fields from them, or you might need to change the names of things slightly, but overall the structure is very similar. So let's go back to the drawing board and think about what we actually need in our code base in the year 2019. If we minimize the amount of code we need to write, then we can significantly increase the speed at which we can deliver awesome software to our users. The first thing we need is a concise but expressive data definition language to describe what the shapes of our various entities are, what fields they have, what types those fields are, and how do those entities relate to one another. And for that, we've already got our create table statement we've already seen. We also need to describe what actions can take place on this table. In Postgres, we might do this with a grant statement, saying which actions you can do. And this is fine for our basic CRUD permissions, create, read, update, delete. But if we need to go beyond CRUD, then there's a way to do that in Postgres by using a function, such as this one, which allows us to flag inappropriate comments. Functions in Postgres can be written in many different languages. SQL, of course, but also Python, Ruby, and even JavaScript in our database. So we've modeled our data types and their relations and the allowed actions on them. But another need that we have is to define exactly which users are allowed to perform these actions and which rows or entities in our database are they allowed to manipulate with them. Now, this is the tricky part. For most of the past 2 decades, there hasn't been a good way of expressing these granular security policies in Postgres. So when people have attempted to solve this problem, they may have used things like views and triggers and functions, or even creating an individual database user for every application user that uses your application. But these methods aren't really a good fit for our modern web applications. They've caused lots of issues and headaches, and this has led many people to say, don't put your business logic in the database. Instead, relying on the application layer to implement these permissions. However, it's key to note that technology advances. It changes and improves. And what was true in the past may not always be true in the future. In fact, the security policies that we need for our modern applications are now a feature that exists in Postgres. It's called row-level security, and it was introduced in Postgres 9.5 not even 4 years ago. Row-level security is very powerful. It finally gives us the ability to express declaratively the granular permission system that our modern applications require. When you define a row-level security policy, the filters defined within it are applied against every table access automatically. And this is not only enforced for directly accessing the table, it's also enforced when you access it through an aggregate, or through a join, or a subquery, or a function call, or any other way that you access that data. And with row-level security, you share just one database role between all your application's users, so it's very straightforward. You can indicate the application user at runtime by just setting a session token in the transaction. So row-level security is very powerful, expressive, and concise. Let's take a look at it. Our first policy starts with the create policy statement, and we give it a name. We want to be able to manage our own comments. It applies to the comments table, and it specifies what actions it governs. In this case, all of the actions. But most importantly, it then gives us a filter. In this case, we want to filter it to only the comments where I am the author. Here we're using a viewer ID function that we defined to find out what the current user's ID is. We might define other policies, like one that says that admins can delete any comment that they want, because maybe it's inappropriate. And also, we have another one that says that everyone can view comments because they're publicly visible. An important thing to note about these is those filters are just SQL fragments. So they can do anything that SQL can do. They can query from other tables in subqueries. They can call functions. They can do various other things. So this looks to be exactly what we need for our modern applications. But when it was first introduced, it often suffered from quite significant performance issues. And this isn't really surprising. Postgres follows a great pattern of software development that you may all be familiar with. Make it work, make it right, and then make it fast. In 2016, with the release of Postgres 9.5, they'd achieved the make it work part and a fair amount of the make it right part. But it wasn't until the release of Postgres 10 in October 2017, just 2 years ago, that they made it fast. The legendary Tom Lane significantly improved the query planner so that well-written row-level security policies no longer have a performance penalty. So we've seen that the past can be informative, but it can also be misleading. anyone who analyzed putting your permissions logic and your business logic into the database before this October 2017 release and found that it wasn't really a good fit was probably right. But this is a conference about the future of software development. It's time to reassess these outdated conclusions. With new legislation such as the GDPR, privacy in the news frequently, and major security breaches seeming to happen all the time, it's becoming more and more important to protect your users' data. Why settle for putting all of this data in a big vault and hoping that no one gets in, or that anyone that you let in behaves responsibly, when instead when in addition you can also have each piece of data have its own protection? With row-level security, if an attacker gets a direct connection to your database, they still can't access other people's data. That's really incredible. So we've learned that the SQL of 2019 can do a lot more to protect user data today than it could in the past. But there are many reasons that we don't want to expose SQL to the client directly. Not least of which is because it doesn't fit the concerns and workflows that web application developers have. They'd still need to abstract this data access, like they do with typical REST APIs, in order to perform their everyday tasks. Can we remove the need for this layer of abstraction with a well-designed API? I think we can. Enter GraphQL. GraphQL encourages us to think in terms of the different entities or nodes in our business domain, their properties and how they relate to each other. These nodes, their properties and the relations between them form a graph, hence the name GraphQL. The query language, the QL, allows the client to query this graph using a query such as this one, retrieving all the data they need and only the data they've requested in a single query, eliminating both under and overfetching. But more importantly, since we can get all the data that we need from the API in a convenient domain object-oriented shape, we typically no longer need the client-side models in order to wrangle it into a more useful structure. We can just use it directly. And because GraphQL is strongly typed and introspectable, our editor can look at our GraphQL API, and it can give us a type ahead to build our query. It can even tell us when we've made a mistake, or show us our documentation right there in line. But it gets better. This query, which we wrote in next to no time thanks to autocomplete, can be automatically converted into type-safe code for fetching the data using something like the Guild's GraphQL code generator. To use this query in a React component could be as easy as this single line of code. This reduces the amount of code that we need to write quite significantly. It makes it easier to write that code, and it eradicates entire classes of errors thanks to the increased type safety. However, building a GraphQL API can be time-consuming, and it has a lot of performance pitfalls you need to be aware of. But this is where the power of Postgres comes in again. Thanks to Postgres' powerful features and strict contracts, we can look at the database and automatically build a GraphQL API by looking at the tables, the relationships between the tables, the indexes on those tables, the data types of our columns, and the constraints, the functions, and the permissions, and anything else that we see in the database. Of course, we don't want to expose every structure in our database, but we can use permissions, hinting, or even explicit instructions to govern what is exposed via our GraphQL API. So a significant amount of our GraphQL schema can be generated from our database, massively reducing the amount of code that we need to write. But this is only one piece of the puzzle. We mentioned before that this is probably only going to work for about 80 to 90% of our domain objects. we also need to be able to add extra types and fields to better express our API. For example, adding custom mutations, or enabling access to services beyond our database, or even integrating with third-party APIs, such as a payment provider. PostgreSQL enables you to accomplish this with schema extensions, or through its powerful plugin system, which enables comprehensive manipulation of how the GraphQL schema itself is generated. Now, once we've got all of this in place, adding this commenting feature to our blog application becomes much more straightforward. In the database, we model the data and the relationships with our table statement. We then outline the actions that can be performed on our table with the grant statement, and we indicate which users may perform those actions with the policies. In the front end, we then write the query that describes all the data that's necessary to render the page. And finally, we write that single line of code that runs the query and fetches the data in a type-safe way. And this is all the code required to model comments and their permissions, and for the clients to fetch them. When the client wants to do mutations, it will be similar to the code on the right-hand side. So we don't need to write by hand the controller logic, the serializers, the routers, the server-side or the client-side models, the data fetching logic, or the cache updating logic. We can solely focus on the parts of the application where our efforts add value, because everything else is standardized and automated. And the icing on the cake is that both GraphQL and SQL are declarative rather than imperative or functional languages. So we can see the entire action that needs to take place ahead of time, and we can plan accordingly. For example, our automated API might turn a GraphQL query such as this one into an SQL query such as this one, fetching all of the data that is needed, and only the data that is needed, in just one query. This allows us to offload the complex task of figuring out how to retrieve the required data in the most efficient manner to software that has been honed over the past 2 decades for exactly this purpose. Modern Postgres even uses genetic algorithms in order to find the most efficient way of executing our queries. So transforming our queries like this can lead to massively increased performance. It also reduces the workload on the database. It enables higher concurrency and reduces our request latency. This delights our users. It pleases the people that are paying the server bills. And it leads to wonderfully fast feature development, which keeps our developers happy too. So by embracing this modern tooling, automation systems, and code generation, we've been able to massively reduce the amount of code we need to write, and we've made it easier to write the code that we do need to. We've reduced traffic, not just from the client to the server, but also between the server and the database, minimizing the number of round trips and the amount of data transferred, and reducing the workload across our entire stack. We've also improved type safety, not just within each of the individual layers, but also between all of the layers, which has helped to eradicate entire classes of bugs. And most importantly, we've increased the speed at which we can deliver excellent software to our users. If you'd like to support or follow my open source endeavors, you can find me on GitHub sponsors or Twitter as Benjie. I also carry stickers and a few cheat sheets, so come and say hi during the conference. Thank you for listening to my talk. It has barely scratched the surface of what is possible with GraphQL and modern Postgres, but I hope that it inspires you to reevaluate your preconceptions and to build things faster than ever before.